Well, today I'd like to welcome to the show Dr. Leslie Kanat. Dr. Kanat is a geologist, and he's also on the Fairewinds Board of Directors. Dr. Kanat, welcome to the show.
Thank you very much.
And of course, Arnie, welcome to the show.
Yeah, hi Kevin, hi Les.
Hi Arnie.
So we've had a lot of reader questions about earthquakes. What are the differences between earthquakes on the West Coast, which we all know about, and earthquakes on the East Coast, which are less frequent? How does that all fit into the nuclear power plant paradigm?
So earthquakes are a result of Earth movement. There are stresses in Earth's crust that when they exceed the rock's strength, then the rock breaks and we get an earthquake. And there are a number of scales that we use to measure. One is the magnitude of the earthquake, and the other is the effects of an earthquake. Now, earthquakes occur all over the planet, yet seem to be most common along plate boundaries. So the west coast of the United States is a plate boundary, and there are numerous earthquakes that occur on the west coast. Yet the eastern seaboard of the U.S. used to be a plate boundary, and there are some seismic zones there that are quite active. What we find that the intensity of the earthquake, that is what one feels, the amount of ground motion, depends on a number of factors, and one is the rock type. So when earthquakes occur on the East Coast, because of the rock type, it's felt for quite great distances, probably 10 times farther than a similar-sized earthquake on the West Coast. As Arnie well knows, of the 104 nuclear power plants in the U.S., most of them, I think all but 8 of them, are what we consider on the East Coast or the eastern seaboard of the United States, and only 8 of them are on the West Coast. It's important to distinguish the magnitude of an event versus what one feels. So the magnitude of an earthquake is determined by seismographic observations. That means the technology that we have in the ground measure how much energy is released by an earthquake. But what one feels, the reactions, the surface expression of these earthquakes are what we call the intensity. By analogy, you can think of the power of a radio station being a magnitude and the strength of the received signal being the intensity. So depending on where you are and atmospheric conditions, you'll have different signal strength from a radio. With regard to the Earth, there's one magnitude for every earthquake, but there are a variety of intensities based upon distance and rock type and depth of focus. The difference between a magnitude 6 and a magnitude 7 means that there are 31 times more energy released in a 7 than a 6. Often people think that there's a difference of 10 times between a 6 and a 7, but the amount of energy release goes up by a factor of 31.
So that 5.8 versus the 6.0 in Virginia makes a big deal difference.
That's about roughly, it's a logarithmic scale, but roughly it's about 6 times more energy released in a 6.0 versus a 5.8. Remember, for every unit, every increment between 5 or 6 or 6 or 7 or 7 or 8, the amount of energy released goes up 31 times. And it takes energy to do work, and the work that's being done is we're moving rock. We're moving large pieces of real estate. Hopefully we're not moving large nuclear power plants.
People are very aware of earthquakes on the West Coast and the potential problems of putting a nuclear power plant on a seismically active area. And really, when we think about it, we think about nuclear power plants on the West Coast. But who's looking at seismicity with nuclear power plants on the East Coast?
There's a group called the Central Eastern U.S. Seismic Source Characterization. It's a group that's put out a really significant, well-thought-out publication back in December of 2011. And the idea there was to look at the relationship of our new understanding of the seismicity in the United States and the presence of nuclear facilities. So I would think that the NRC, the Nuclear Regulatory Commission, and the U.S. Geological Survey are aware of these issues. And indeed, what's happened is, as a result of this study, is we found that the likelihood of some problem has gone up many times, several-fold. Indeed, I think they report that the estimated risk of a problem at a nuclear power plant on the East Coast has tripled based upon our new understanding of seismicity along the East Coast.
So, Les, as an engineer, what I want to know is, what's the worst earthquake I have to design against. And let's take a look at the one in Virginia. That was designed for a 6, and the quake that actually hit was a 5.8. So, to my way of thinking, that was close, but it survived. But when you build a nuclear power plant, you don't want to build for the earthquake that is going to happen, because you've got the low probability, high consequence events like the tsunami at Fukushima you have to worry about. So when engineers are told by geologists that a 6 is the worst you can expect in Virginia, and all at once a 5.8 actually happens, does that make you question whether or not you could actually have an earthquake more than a 6?
There are several issues you raised there. One is, again, just because it is a certain magnitude doesn't mean that that's what one is going to feel. The difference between how big an earthquake is and the intensity depends on a lot of issues. So if the magnitude 6 event was closer to the power plant, or the rock type, or it was transmitted through the rocks in a different way, then a magnitude 6 could do a lot of damage, where another time magnitude 6 a little farther away, a little deeper, on a different fault, even on a different fault the same distance away, might do no damage. So it's more than just looking at the size of the seismic event. It has to do with the location and the long-term history. What we've done in this recent work on reviewing the seismic risk on the East Coast is we had chosen a time period for which we're going to look at the seismic events. The Virginia quake of August of 2011, the 5.8 quake, which is probably the second largest in this region, wasn't included in the data set. So if it was included, I would think that the risks of accidents or damage to facilities on the East Coast would have been greater. So I think, Arnie, in answer to your question is, all of us are short-sighted and all of us have deadlines. So how far back in time do we want to look, as well as at what point do we say we have enough data to make our choices? And it's risk assessment.
Now, I can remember pictures of the spent fuel casks at North Anna, which was the power plant nearest to the earthquake. And these casks weigh more than 100 tons. And you could see where the cask had been on the pad, the concrete pad, and you could see where the cask had moved. And these 100-ton casks were displaced by 4 or 5 inches. Now, the press reported that as the cask moved, but for the physicists out there listening, really, it's like sliding a tablecloth out from underneath a plate on your table. Yeah, the cask didn't move at all. The ground moved 6 inches sideways.
Well, yeah, that's the basis behind the seismometers that we use, is that we no longer use a pendulum, but if we had a pendulum fixed on an apparatus and the ground moved, the pendulum would remain motionless and the ground beneath it would move. So sure, what you said is a good way to think about it. The acceleration of the ground is what we measure when we think about earthquakes, is how fast is the ground moving relative to a stable object, and having massive dry cask would certainly want to stay in place as the ground shifts beneath it.
When you build a nuclear power plant, you have to worry about how fast the ground moves, but then you have to move that wave up in the building. The higher up in the building you are, the more sway you get in the building. And that's something called the amplified response spectra. The higher up you go, the more the building wiggles. Well, on plants that are this Mark I boiling water reactor design, they've got this enormous weight, the nuclear reactor, and the other enormous weight, the spent fuel pool, way up high in the building. So these Mark I reactors actually pose more of a seismic risk. They're harder to build than other designs where the weight is lower.
So, Arnie, are power plants on the West Coast designed any differently than the power plants on the East Coast because of different seismic circumstances?
Well, the nuclear reactors themselves are essentially identical. But the more serious the earthquake, the more serious the bracing that goes around the nuclear reactor, like shock absorbers on a car. But the question is not, are they built stronger on the West Coast, but have they anticipated the worst earthquake imaginable as opposed to the worst earthquake that happened in the last 100 years? I think what Les said is really important, that you have to go back in history long enough so that you get a proper risk assessment. I really, as a design engineer, I don't care what happened in the last 100 years. I care about what happened in the last 10,000 years because I'm building against a low probability but high consequence event.
Correct. And I think in addition to what you said about the resonance frequency with regard to the height of the building, when an earthquake occurs, it releases different types of seismic waves with different types of vibrations. And they have different periods, different vibrational frequencies. Some affect low-rise buildings more, some affect high-rise buildings more. It also depends upon the distance as to if taller or shorter buildings are affected. As structures age, they become weaker. I think about my automobile, my car, that the older it gets, the more work I need to put into it, and the less likely I am to run over a bump in the road and feel it'll be okay when I come off the other side. So as our nuclear power plants age, the effects of the same magnitude event might be a little more damaging.
You know, we see that at the Seabrook plant where the concrete is degrading very rapidly because there's salt in the underlying soil that the plant is built upon. So that the margin that it used to have 20 years ago when it was built is dramatically reduced now. So we wind up eating into design margin as a plant gets older. Any plant can be made to withstand any earthquake, but it boils down to money. And if you believe a 7 is possible on the East Coast, you're going to build a plant much stronger than the East Coast plants are presently built to withstand. You know, the plant in Virginia that was right next to the earthquake was built for a 6, and it had a 5.8. And of course it survived because that's what the engineers designed it for. But the real issue is the 6 the worst that can be expected on the East Coast? And should we really have designed the plant for a much more rigorous standard? And that's where, in my mind, the East Coast plants are in jeopardy. They're built for these Richter 6s that we know can happen now with Virginia. And if a Richter 6 can happen in 20 or 30 years of a nuclear plant's life, then a Richter 6.5 might happen over the duration all these plants are designed to operate.
So, Les, have we ever seen anything 7 or greater on the eastern seaboard?
In the eastern part of the United States, there's a really high-risk area that has the potential for lots of ground motion in the New Madrid, Charleston area. Back in 1811, the late December of 1811, there was a 7.7 event, followed a few weeks later by a 7.5, and a few weeks later by another 7.7. So these events in the New Madrid seismic zone are common. Indeed, they occur every few hundred years. The last significant event in that area was May of last year, May of 2011, I think it was. There was a 7.7 earthquake again. There are a large network of faults there from a rift that formed 500 million years ago. If we look at the location of the current nuclear power plants, both the commercial reactors and the research reactors, there aren't any that are on the New Madrid seismic zone. You could see they almost make a circle around it because we do recognize that is an area of high risk. But what we don't do is we don't go back far enough in the geological record and take the long view of what might happen. If you think about a business plan, when businesses make a plan for their future, they plan maybe 5 years out, 10 years at the most. Geologically, it's meaningless. We've got to take a much longer view and look at worst case scenarios because indeed they will occur, just the probability is low.